Hello. Uh, Today in this lecture we are going to continue with the series on matrices, and today we are going to discuss in detail some eigenvalues and eigenvector problems. Also that we are going to study eigenvalue and eigenvalues and eigenvectors in particular for some special matrices like Hermitian matrices, unitary matrices, and likewise. So I hope people have joined in. I'll wait for a minute and then we shall start. Okay, just a little bit of correction from yesterday's lecture. I think I made a mistake here. So I was yesterday telling that the eigenvalues of a triangular matrix are the diagonal entries. They are nothing but that they are the diagonal entries. Okay, these are your eigenvalues. Okay, now uh, there can be two kind of triangular matrix. One is called as a lower triangular matrix, and other one is called as upper triangular matrix. Okay, Okay, now the matrix that I showed you, it's not lower triangular, rather it is upper triangular. So I think I made a mistake yesterday. Please correct it in your notes. Uh, it is this particular matrix where this triangle, let's say, are you getting my point? So all these entries I'm not talking about, I'm talking about these entries. If these are zero, then I would say that this is an upper triangular matrix. Just correct it in your notes, okay? These are called as upper triangular matrix. Okay. And if the same scenario appears on the like this way, if this is a matrix, and let us say this is your diagonal elements, these are your diagonal elements, and if these are zeros, okay, these are zeros, then this is called as the upper triangular matrix, then this is called as a low triangular. Okay, but overall understand whether it's upper triangular or it is low triangular, the eigenvalues for the triangular matrices are nothing but the diagonal entries. Okay, so you don't need to pay, you don't, whenever you see such a matrix, don't try to find the eigenvalues, just write the diagonal entries. So the diagonal entries are themselves the uh, you can say the eigenvalues. So basically what are triangular matrices? Where the, like for example, if I'm talking about upper diagonal, then the entries, I can write entries, this is the principal diagonal, below the principal diagonal, below the principal diagonal are 0. So entries below the principal diagonal are 0, then this is called as upper diagonal matrix. Okay, and if the entries above the principal diagonal are 0, then it is called as a lower triangular matrix. So please correct it in your notes. Overall, I wanted to explain that eigenvalues of a triangular matrix are nothing but the diagonal entries. I think it was with respect to this question I stated. Okay, I wanted to find the trace of m raised to power 20, and where m is given by 210, 020, and 003. Okay, so let us do a few more questions in order to strengthen our understanding. Let us strengthen our understanding by doing a few more questions. I hope people have joined. Please let me know who have joined by actually remarking. Let's make a trend that whenever anybody joins, please mark a present on the chat box so that at least I'll be aware. Uh, Kindly mark a present on the chat box so that I'll be aware, and then we'll start. Okay, now just give me a question. Just give me an answer to this question. If each entry of an n cross n matrix, if each entry of an n cross n matrix is a real number, then eigenvalues of A are all real numbers. True or false? Just let me know, true or false. So I'm giving you a question. Uh, okay, so Arpita has come, Anshul has come. Okay, so this is now the regular trend. Whenever you're going to join, please, so you have to just mark a present so that it remains a tradition, and I'll be aware of how many people have joined. Okay, so what do you think? Is it true or false? Is it true or false? What do you think? If each entry of an n cross n matrix is a real number, then the eigenvalues of all are all real numbers. Is it true or false? So if all the entry of n cross n matrix is all the entries of an n cross n matrix is real, then the eigenvalues are all real numbers. True or false? What do you think? I mean, are there any answers from the audience? Okay, so let me give you an answer to this. So answer is false. Why answer is false? See, understand. Just take any 2 cross 2 matrix. For example, just take any 2 cross 2 matrix. And I know that for 2 cross 2 matrix, the equation, the characteristic equation would be a quadratic equation. The characteristic equation would be a characteristic equation would be a quadratic equation. Do you always think that quadratic equation has real roots? Do you always think that quadratic equation have a real root? Do you always think that quadratic equation has a real root? Answer is no. So in general, always remember, it's not necessary that if all the elements of a matrix are real, then the eigenvalues are also real. No, that's not the case. Okay, so just take an example and you'll be able to understand what I want to say. Let us take an example to understand what I want to say. Let us say, take example b is equal to, yesterday also I took an easier example. I took yesterday this 1 1 0 and 0. If I take this example, what I will get? Take a minus 1 here, so I'll get no, not take minus 1, it will be fine. So the characteristic equation will be minus lambda square. I think you take a minus lambda square minus of 1 equal to 0. So if you find the characteristic equation, it will be equals to what? It will be equals to minus lambda square minus 1, which implies lambda will be equals to what? Plus minus of iota. So all the entries are real, but the eigenvalues are imaginary. So it is no guarantee that if all the entry of the all the entry of an n cross n matrix are real, then it does not necessarily imply that eigenvalues have to be real. Okay, they may be imaginary as well. I hope it is clear. Another example you can take, let's say 2 minus 1 5 and 2. Just find same and you'll be able to find that the eigenvalues would be. So for example, if you want to take this example again, you see This has been strategically created because 2 2 will give you, this will be 2 minus lambda whole square. I think I should take minus 2 then, only then it will matter. Okay, so let us take minus 2 here. Okay, so this will be 2 minus lambda into 2 plus lambda with a negative sign, and then plus a 5. Plus a 5 equals to 0. And what it will be like lambda square minus minus plus, so this will be lambda square minus 2 lambda and plus 2 lambda, which will be 0, and there would be minus 4 plus 1. So minus 4 and plus 1 is equal to this. So lambda square plus 1 equal to 0. It implies lambda is equal to what? Lambda will come out as plus minus of iota. Lambda will come out as plus minus of iota. I hope it is clear. And this is my request. Anybody who's listening to the lecture, we get 0 right. Okay. So so 5 people have joined. I have written already that whosoever joins, please type present once you enter the class. I mean, this, make this a tradition so that I'll be able to understand whosoever is coming. And secondly, the question that I asked was, for those who have joined right now, question was, if each entry of an n cross n matrix is a real number, then eigenvalues of A are all real numbers. Answer is false. Okay, answer is false. Example I have given. Is that clear? Now try to do another question that I'm giving to you. Now I'm giving another question. I hope you'll be able to do it. I have taught you much of the concepts regarding this. So question is, if A is a 5 cross 5 matrix, if A is a 5 cross 5 matrix, if A is a 5 cross 5 matrix, if A is a 5 cross 5 matrix with such that trace of A is given to be equivalent to 15, and 2 and 3 are eigenvalues of A, with multiplicity, with algebraic multiplicity, 2, then the determinant of A is equal to. Then the determinant of A is equal to. This is what I am asking. Okay, and I taught you yesterday algebraic multiplicity or in general multiplicity, because after a while I'll talk of something called as geometric multiplicity also. So therefore to mark a distinction, I have used the word algebraic multiplicity. By algebraic multiplicity, we in general what I told yesterday. So just to recollect yesterday's lecture, I told you that, what did I tell you? I tell you that if A is an n cross n matrix, okay, if A is an n cross n matrix and satisfies Ax is equal to lambda x, let us say this is your eigenvalue equation, and the characteristic polynomial to this particular equation, will be what? So the characteristic polynomial to this would be a polynomial of degree n. Will be a polynomial of degree n. So polynomial of degree n will be a characteristic polynomial, and it is not always necessary now. It is not always necessary that each root will come once only. Who says? It may so happen that, let's say the polynomial is, let us say the polynomial is lambda minus 2 whole square into lambda minus 3. So here you can see that 2 is of multiplicity 2. So if I factorize this particular characteristic polynomial, I yesterday also told you, if I factorize this particular characteristic polynomial, and let us say I get lambda minus lambda 1 raised to power, let's say some n1, lambda minus lambda 2 raised to power n2 dash dash dash, lambda minus lambda k whole raised to power nk, such that lambda 1, lambda 2, lambda 3 dash dash dash, lambda nk are different eigenvalues. These are what? Are eigenvalues. Then this particular exponent, that is n1, represents your multiplicity, algebraic multiplicity. So then algebraic multiplicity, see here lambda minus 2 whole square written, so it implies what? The algebraic multiplicity of the eigenvalue 2 is 2. So here lambda minus lambda 1 is written and raised to power what? N1. So then the algebraic multiplicity of lambda i's are simply ni's. Okay, so please remember, this is what I told yesterday, and again I'm telling you here also. So it is given that the trace of matrix is 15, and 2 and 3 are those eigenvalues which have algebraic multiplicity of 2, Then the determinant of A is equals to what? Please let me know what would be the determinant of A. What would be the determinant of A? What would be the determinant of A? So the determinant of A, how to find? I told you yesterday that whenever we have to find the determinant of a matrix A is nothing but it is equals to what? It is equal to the product of eigenvalues. It is equals to what? It is equals to the product of eigenvalues. It is equals to the product of the eigenvalues. And what is the trace of A? Trace of A is the sum of eigenvalues. Trace of A is the sum of the eigenvalues, if you remember. Okay. So now I already know that my matrix is such that the trace is going to be 15, and the eigenvalues are 2 is repeated with 2 is also repeated and 3 is also repeated. So 2 is also repeated and 3 is also repeated. And now I can write here lambda. Okay, so I can now write here lambda. So what does it imply? 3 plus 3 is 6, 6 plus 4 is 10. So lambda would be equals to what? 5. So the other eigenvalue would be simply 5. Now we have to find the determinant. Determinant is what? It is equals to product of eigenvalues. The product of eigenvalue will be what? 5 into 2 square into 3 square. So what is 2 square? 4. 4 into 5 is, I think, 20. 20 into 9 is 180. So answer should be 180. I don't know why 6 is coming. Answer should be 180. I hope it is clear. I mean, is that question clear now? I think okay. So this is it. I hope it is clear. Now I'm moving to another question. Okay. Okay. So this was easy. I think. And now let us do a few more other questions in this section only, and then you will be able to understand what I want to convey. Only then you will be able to understand what I want to convey. Okay, now do another question that I'm giving to you, and it is more than one option correct. Okay, it is more than one option correct. So that you'll be able to get what I'm saying. You'll be able to get what I'm saying. So I'm saying that okay. So let us say that there is a matrix. Just give me a minute. I think there is a problem with this. Okay. So now see, there's a now I'm doing a question for you. I'm writing a question for you. Please try to understand. Okay. The question says that let lambda and mu be the eigenvalues of a 2 cross 2 matrix, a 2 cross 2 matrix A, a 2 cross 2 matrix A, then which of the following statement is true? Then which of the following statement is an R true? Okay, option number 1, A square has distinct eigenvalues. A square has distinct eigenvalues. Okay, this is the first option. Second option is A cube is equals to lambda whole cube minus mu whole cube divided by lambda minus mu A minus lambda mu into mu plus lambda times identity. Option number C, trace of a raised to power n, trace of a raised to power n is equal to lambda raised to power n mu raised to power n for every positive integer n. And option number D, a raised to power n is not a scalar multiple of identity. A is not a scalar multiple of identity. I think I've given a question whereas okay, so there is, I think everybody's in MSc class, so probably everybody must be knowing Kelly-Hamilton theorem. Although I'm going to do it slightly next to this topic only, but just let me know if you know the Kelly-Hamilton theorem. Every matrix satisfies its characteristic polynomial, if you remember. So every matrix satisfies its characteristic polynomial. So this is the Kelly-Hamilton theorem. So let's say you get a you get a matrix A and you find a characteristic polynomial. If you replace instead of the lambda, that is the variable for the characteristic polynomial, instead of the variable of the characteristic polynomial, if you replace it with A, then A, that is a matrix, always satisfies its own characteristic polynomial. So please do remember. I think this is something that everybody knows. If you do not know, I'm writing it here. Always remember that I think probably in this statement it may be applied. So therefore I'm doing. So every matrix satisfies its characteristic polynomial. Every matrix satisfies its characteristic polynomial. Now let us think about this question. So see the question that has been given to you. So at times in examination you have to be slightly tricky. It says that let lambda and mu be the eigenvalues of a 2 cross 2 matrix. So lambda and mu are what? Eigenvalues of a 2 cross 2 matrix. It says that A square has distinct eigenvalues. Why? It is not always necessary. Let us say that the matrix A has 2 eigenvalues, and those 2 eigenvalues are, let's say 1 and let's say lambda is equal to minus 1. And yesterday I told you that if A has the eigenvalues lambda, then A square has eigenvalues lambda square. Then the eigenvalues of A square would be lambda square. And what would be lambda square? Minus 1 lambda square is 1. Mu which is equal to 1. So 1 square is also 1, minus 1 square is also 1. So I can write that the eigenvalues of A square would be simply 1. So it is not necessary that if A has distinct eigenvalues, sorry, if A has you have been given A having distinct eigenvalues, it is not necessary that A square will also have a distinct eigenvalue. It may so happen that one of the eigenvalue happens to be 1 and other happens to be -1. Then what? Is that clear? So option number A you can straightway disregard. Your option number A you can straightway disregard. Okay, now you see what has been given to you for a 2 cross 2 matrix. Just think about it. Just think about it. I'm just writing it here. So just think about it. Just think about it. If I'm saying that A is a 2 cross 2 matrix, A is a 2 cross 2 matrix. If A is a 2 cross 2 matrix, then the you can say the I can say the characteristic equation would be a quadratic equation, right? And if characteristic equation is a quadratic equation, then I know that if I have the roots lambda and mu, then I can make the corresponding quadratic equation to this. The corresponding quadratic equation would be what? X square minus lambda plus mu x plus lambda into mu equal to 0, right? So if your A is a quadratic, if your A is a 2 cross 2 matrix, then the characteristic polynomial will be a quadratic equation and whose roots are given to be lambda and mu. Okay, because the roots of the characteristic polynomial itself are the eigenvalues now. So if you have the roots, then you can easily make the quadratic equation. So this will be your, I can write, this will be your characteristic equation. So I'll write characteristic equation of A. CH means characteristic equation of A. Is that clear? And I know that from KellyHamilton theorem. I'll however tell the KellyHamilton theorem. Just excuse me, because actually I introduced the question before the concept. So I'll do the concept later on. But I hope everybody is in MSc, so everybody must be knowing KellyHamilton theorem. So this characteristic equation is satisfied by the matrix itself. So I can write A square minus lambda plus mu times A. Sorry, x should also x in place of x you have to write A and then lambda into mu. And times identity must be equal to what? Must be equal to 0. Okay, so always remember this is called as the KellyHamilton theorem. KellyHamilton theorem says what? Every matrix satisfies its characteristic equation. So every matrix A satisfies it. Every matrix A satisfies its characteristic equation. So if your characteristic equation is this, then A would always satisfy this. Is that clear? Now you see, just think about it. If this is the case, then think about, if I multiply this entire thing by, if I multiply this entire thing by A, if I multiply the entire thing by A, then what will happen? Or what should I do? I mean, this what was given to us. I think I should play with the options. Only then I'll be able to make some sort of statement. So characteristic equation of A is given to be equals to A square. Sorry, characteristic equation is given to be this, right? Characteristic equation is given to be this. So if A is given to A would satisfy this characteristic equation, right? And the options are given to us in a slightly different manner, right? Options are given to us in a slightly different manner. Then we'll have to see about. Okay. So let us think about the option number 2 later on. So let us drop the option number 2. This is something that I can conclude. This is something that I can conclude till now. Okay, we'll think about it later on. Now just think about option number C. Just think about option number C. What do you think? What do you think? If A has the eigenvalues lambda and mu, then the eigenvalues of a raised to power n would be what? Eigenvalues of a raised to power n would be simply lambda raised to power n and mu raised to power n, isn't it? The eigenvalues of eigenvalues of a raised to power n would be what? It will be equals to lambda raised to power n and mu raised to power n. So trace a raised to power n would be equals to what? Trace a raised to power n would be lambda raised to power n plus mu raised to power n, isn't it? So option number C is correct. That is absolutely right. What do you think about option number D? Option number B, I'm doing after this. First try to do this. First try to do these last two statements. The first statement is incorrect. That is very much clear. I told you it is not necessary that if A has distinct eigenvalues, then A square should have a distinct eigenvalue. No, it's not necessary. Option number C is also correct. Option number C is correct because if lambda and mu are the eigenvalues of A, then for a raised to power n, the eigenvalues will be lambda raised to power n and mu raised to power n. So trace a raised to power n would be lambda raised to power n plus mu raised to power n. I hope it is clear. Please try to do the option number D first and then we'll move to option number B. Just think about option number D. Just think about option number D. Okay, nobody's getting something. Okay, so option number D says a raised to power n is not a scalar multiple of identity for any positive integer n. The option says that a raised to power n is not a scalar multiple of identity for any positive integer n. So okay, I'll help you out. So I started with this particular thing. If you remember, I started with a matrix. For option number A. What did I do? I told that let us take a matrix A which has both the eigenvalues plus minus 1. Okay, so let us construct a matrix. Let us say a diagonal matrix. So I'm taking a diagonal matrix minus 1, 1, 0, 0. Clearly, if I'm taking a diagonal matrix, then the diagonal elements are only the eigenvalues, right? If you do A square, I told you if you do A square, what you will get? You will get 1, 1, 0, 0. This is something that you should be able to relate. Now, how can I say that? How can I say that a raised to power n is not a scalar multiple of identity? Clearly it is. Clearly it is for any positive integer. Why? If A is a 2 cross 2 matrix, who stops me from taking this as a matrix A? And if I do an A square, what would I get? I'll get an identity. So a raised to power n can indeed be written as k times identity. It indeed can be written as k times identity. Please let me know if you're getting this. If you're not getting this, then I'll lower down the level. Okay, we'll do questions from your exam also. But please do understand these are also important questions as such. For scalar matrix, diagonal element should be like the same. Okay, so what I was telling is actually see what I was telling was, see, if I'm saying that option number D, and what I was saying, see, understand my point that if the question was very simple, lambda and mu are the eigenvalues of 2 cross 2 matrix, fine, and then a square has a distinct eigenvalues. No, it does not have a distinct eigenvalue. Okay, now, it does not necessarily have a distinct eigenvalue. Why? Because if you take a to have eigenvalue -1 and +1, okay, just take eigenvalues -1 and +1. So I know that if a has eigenvalues -1 and +1, then a square will always have an eigenvalue of lambda square, right? So eigenvalues would be 1. For a diagonal matrix, the eigenvalues always lie on the diagonal. For a diagonal matrix, that is quite easy to see that the eigenvalues will always lie along the diagonal only. For diagonal matrix, the eigenvalues will always lie along the diagonal. Okay, so the diagonal elements represent nothing but they represent the eigenvalues. Okay, now just take the first example, 1 minus 1. If these are the eigenvalues, can I not make the matrix in this form? So this will be the matrix, right? This would be the matrix A. And if I do an A square, I'll get an identity. So it negates our option number D, because option number D says what? A raised to power n is not a scalar multiple of identity. Who says? No, it. Also understand that if A's eigenvalues are lambda and mu, then A raised to power n eigenvalues would be lambda raised to power n and mu raised to power n. And trace A raised to power n would be what? It would be lambda raised to power n and mu raised to power n. I think it is quite easy to see. Now just coming back to the option number B. As I told that this would be the characteristic equation. If this is the characteristic equation, and what was asked, actually the option number B was asked in A cube. So what I can do, I can multiply this equation by A. So if I multiply this equation by A, what I'll get? Lambda cube minus lambda plus mu. And here what is written? I think it will become A square here, and plus lambda into mu times A is equal to 0, right? Is that clear? Now what I can do, I already know what is my A square. I know that my A square is, I'm writing it here, my A square is what? My A square is simply minus lambda mu identity plus lambda plus mu times A. So just replace this A square here. What you will get? You will get A cube minus of lambda plus mu. What is your A square? A square is minus lambda mu identity plus lambda plus mu or what should I do? I think I should be basically, now here I'm not getting an answer, right? So option that was given to us was in A cube, right? Option that was given to us was in A cube. Okay, so rather you can do this also, right? You can do this also instead of this, because we were given this option now, so we can do this also, right? Instead of doing this, we can do this also, because from here we are getting minus lambda square and mu square, and that is not going to help us anyhow. That is not going to help us. So what I'm going to do is, see, what I'm going to do is, okay, what I'm going to do this, see, okay, so I'll do what, let me write this as equation number 2, and let me write this as equation number 1, so that things are easy for me to understand. Now what you can do, replace this A square here. So then what will happen? Then you will have all the options in A cube, A and I. Okay, see, what I want to convey is, see here, in option itself it is clear that A cube is represented in terms of A and I. Okay, so A cube is written in terms of A and I. So what I'll do one thing. Here I know A square is given to us. A square is given to us, right? If I replace this A square here, so what I'll get? I will simply get just think about it. So if I replace A square here, what I'll get? So A square would be equals to A cube divided by, so this will give you lambda plus mu here, A square lambda plus mu divided and plus lambda mu A divided by lambda plus mu, right? So this is how you can write your A square, right? I think this is quite easy to see. And if I replace it here, what I will get? So if I replace it here, I'll get a cube divided by lambda plus mu, and then plus of lambda mu. I think it is a very lengthy question. Okay, koi baat nahi. We'll see. No issues. And then I will have a minus of lambda plus mu a, and then plus of lambda mu identity is equal to 0, right? Is that clear? I hope it is clear. Now what will happen? Now what will happen? See, if this is the case, then what will happen? If this is the case, then what will happen? See, if this is the case, then what will happen? Just try to take this lambda plus mu all both of the sides. What you will get? There is some issue with the question. I don't know what has happened. If I multiply with product of matrix, right? So A is fine. So that is fine, but I think there is an issue with the option number. I don't know what is the issue. Chalo, koi nahi, let us see. So what I will get? I will simply get from here a cube to be equals to what? I will simply get a cube to be equals to what? I think this lambda plus mu would go here, so I'll get a negative of lambda plus mu into lambda mu identity, right? This is 1. This is 1. And then what can I write? And here it is what? Here I can write lambda plus mu. So this will go in this side, and lambda plus mu whole square a minus lambda mu into lambda plus mu a, right? I hope it is clear. I hope it is clear. So what will happen? I can write that my a cube is equal to, this would be lambda square plus mu square I think then I will have a minus of lambda mu, right? Okay, so I'll have only minus of lambda mu, right? Because if I multiply lambda plus mu on both sides, then I will have this, and it will have simply this minus lambda plus mu into lambda mu times identity. So I can write that my a cube would be equals to what? My a cube would be equals to, if I multiply both sides like above and below by lambda minus mu and lambda minus mu, what will I get? I can simply write that as what is happening? What is wrong? That is okay. This square will also give me 2 mu u, right? So it will be plus here. See, this would be lambda square plus mu square plus 2 mu lambda, and minus lambda mu will come from here, so you'll get a lambda mu. If I multiply both numerator and denominator by lambda minus mu, you'll get lambda cube minus of mu cube divided by lambda minus mu times a minus lambda mu times lambda plus mu identity. Okay, so option number B is also correct. Option number B is also correct. I hope it is clear. Please let me know in the comment section at least that you are getting or not getting. Just be receptive. Just be receptive on the comment section, because otherwise I'll not be able to understand that are you getting or not getting. So I hope it is a slightly difficult question, but overall such questions may not be asked in your examination, but just for practice, I gave you a question where each of the concept you can apply. Now let us move to an important topic which is called as the KellyHamilton theorem. Let us move to the topic. Okay, good. Okay, so secondly, let us now write another theorem which is called as the KellyHamilton theorem. So let us write about KellyHamilton theorem. What does it say? What does KellyHamilton theorem say? KellyHamilton theorem, as I wrote above, it says that every square matrix satisfies its characteristic equation. So every square matrix satisfies its characteristic equation. Okay, so in general I can write every, and in physics most often we are going to deal with square matrices only. So, okay, so in every matrix satisfies its own characteristic equation. Every matrix satisfies its own characteristic equation. For example, if I'm giving you a matrix, let's say 1 2 3 4, 1 2 3 and 4. Okay, if this is your matrix M, then if I want to write the you can say secular determinant, the secular determinant will be m minus lambda mu is equal to 0. And if I do m minus lambda mu is equal to 0, lambda mu m minus lambda I mod equal to 0, then what I will get? I will simply get 1 minus lambda into 4 minus of lambda minus of 6 equal to 0. Okay, minus of 6 equals to 0. This is one thing. And if I solve this particular thing, what will I get? I will simply get lambda square minus 5 lambda plus 4 minus 2. So I'll get my lambda square minus 5 lambda minus 2 equal to 0. Okay, now this is your characteristic equation. What does Kelly-Hamilton theorem say? Kelly-Hamilton theorem says that if I replace my A instead of this, then this would be satisfied. Let us see. It is easy to verify for this matrix. Let us see. A square minus 5 of A minus 2. Let us verify for this. Let us verify our Kelly-Hamilton theorem for this. What would be A square? A square would be simply, I'll write it here, 1 2 3 4, and again write 1 2 3 and 4. Okay, what would be 1 2 3 4 5 6 7 here, 6 8 9. So I'll get a 9 here, 10 here, sorry, 10, sorry, and then I will get a 15, and then I will get, I think, 22, right? So I think this would be A square. It's quite easy to see that A square would be 7 10 15, and here you will have a 22 minus 5 of A. So what will be 5 of A? 5 10 15 20, and then minus of 2. This 2 can be replaced by 2 times identity here. Okay, so 2 times identity. So 2 times identity will be minus 2 0 0 2. So what you will get finally, 7 minus 5 is 2, and I think it is quite easy to see that this will be a null matrix. So always remember that characteristic equation is satisfied by the matrix of whose characteristic equation is it. So for example, if A's characteristic equation is something, then let's say it is CHX is the characteristic equation of a matrix A, then it is the matrix also satisfies the characteristic equation. So if characteristic equation is CHX, then if I replace A instead of X, then it is fine. Then this is what your Kelly-Hamilton theorem says. I hope it is clear. Please let me know in the comment section that is it right? Is it something that you're following or not following? Okay, is that something you're following or not following? Please let me know. Okay, so I told you on the very first day that if I have this, let's say this is my coordinate axis, and let's say this frame is S, and if I rotate this frame, okay, good. So if I rotate this frame by some theta angle, and let us say this is S dash, then the coordinates in this frame, that is S dash, can be written in terms of coordinate in S by the help of a rotation matrix. So 2 cross 2 rotation matrix will be responsible for dictating the rotation in 2-dimensional space. A 3 cross 3 matrix would be used when we'll have a 3-dimensional rotation. So just for now, I'm saying that let's say this is a 2 cross 2 matrix. This represents your rotation. So just verify your Kelly-Hamilton theorem for my rotation matrix. Just verify it. I think this is an exercise for you. Just try to do it. Just try to do this. Minus sine theta and cos of theta. Just think about it. What do you think that, so this is your rotation matrix. Now let us first find the eigenvalues for it. So eigenvalues for it would be what? So eigenvalues would be cos theta. I have to write minus, I'm just writing the determinant directly. So it will be cos theta minus lambda whole square, and then this minus plus, there will be plus sine square theta equal to 0. Okay, now if you find an answer to this, what you'll get? You'll simply get lambda square minus 2 cos theta, and then you will have a plus 1 equal to 0, right? Lambda minus 2 lambda cos theta plus 1. And if you solve this up, what you will get? You will simply get lambda is equal to 2 cos theta plus minus root over what? Root over 4 cos square theta minus 4 divided by b square minus 4ac divided by 2. So your answer should come out as lambda is equal to cos theta plus minus of iota sine theta. Always remember this. This is quite famous. So always remember the eigenvalues for this equation. Eigenvalues for these equations are lambda is equal to e raised to power plus minus iota theta. This is something I just told you for the sake of telling you. So always remember that for the rotation matrix 2 cross 2, the eigenvalues are lambda is equal to e ki power plus minus iota theta. Now let us verify our Kelly-Hamilton theorem. So what is your characteristic equation? So I'm writing that characteristic equation is given by lambda square minus 2 of lambda cos of theta, and then you have plus of 1. So instead of lambda, I have to replace what? I have to replace my rotation matrix. So rotation matrix is R. I'll write R square minus 2R, and then I have this cos of theta, and then instead of 1 I can write identity here. Okay, instead of 1 I can write identity here. And what is R square? R square would be simply, just find what would be R square, cos theta. I think cos theta, then sine theta here, and then you'll have this minus of sine theta, and then you have this cos of theta. And if you do a R square, what would be R square? Just find it finally. Cos theta, sine theta, minus sine theta, cos of theta. So just find this. So this will be cos square theta minus sine square theta. I'm writing cos square theta minus sine square theta here. Then this will be, I think 1. I think 1 nahi. 2 cos theta sine theta. So it will be 2. I think I should write sine theta cos theta. And then this would be minus 2 cos theta sine theta. And then the last one would be again cos square theta minus sine square theta. And then you just think about this. What would be minus 2r cos theta? So it is equivalent to writing minus 2 and this. So it will be minus 2 cos square theta minus 2 sine theta cos theta. And then I think I should write not minus right now. Okay, so if I'm writing minus here, then I should refrain from doing so. So it will be minus 2. This is a minus here. Okay, sine theta cos theta, and then I have again some 2 cos square theta here. Okay, and then plus identity. So instead of identity, what I'll write cos square theta plus sine square theta here. Here I'll write 0, here I'll write 0, and here also I'll write cos square theta plus sin square theta. So now it is easy to verify that if this is minus, this will become what? Minus 2 cos square theta. I think this is quite easy to verify that I will get a null matrix. Is that clear? So I have verified your Kelly-Hamilton theorem, although I have not derived it because the derivation part I'm not doing it. I'm not giving you the proof for the Kelly-Hamilton theorem. I have actually somehow made you understand this Kelly-Hamilton theorem through two of the examples. One of the example is your rotation matrix, and one another example I took. I hope you're getting it. Please let me know in the comment section if you're getting it or not. And if you're not getting it, kindly let me know. Please let me know if you're getting it. Okay, chalo, let us move further. Now, you would be thinking that what is the utility of teaching this Kelly-Hamilton theorem? So, the first application that you can think of is finding an inverse. So if I want to find an inverse of a matrix, then this Kelly-Hamilton theorem is very handy. It's very handy. How come? Let us say I am finding this a minus lambda I mod equal to 0. Okay, I am finding this secular determinant, that is a minus lambda I mod is equal to 0. Now what will happen? Let us say that it generates me a you can say a characteristic polynomial Cn into lambda raised to power n plus Cn minus 1 raised to power lambda n minus 1. Let us say Cn minus 2 lambda raised to power n minus 2 and dash 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 dash, and at the end you are getting C1 lambda, and then you are getting C naught. Let us say this is your characteristic equation that you are getting. As I told you, this characteristic equation is satisfied if I replace lambda by a. So if I replace lambda by a, then this characteristic equation is also satisfied. So I'll get Cn a raised to power n plus Cn minus 1 a raised to power n minus 1 plus Cn minus 2 a raised to power n minus 2 dash 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 C1a plus C naught is equal to 0. Now if I want to find an inverse, what I can do, I can throughout pre-multiply it with A inverse. So I can multiply from left A inverse. If I multiply from left A inverse, I can get that my A inverse, this would be, here I can write A inverse, here I can write A inverse. So A inverse will be equals to what? It will be equals to minus 1 upon C naught Cn a raised to power, I think it should be a minus 1, then Cn minus 1 a raised to power n minus 2 dash dash dash, and then you will get C1 into identity. I hope it is clear. I hope it is clear. Please let me know if you're getting it right. So this is how this becomes very handy. So for example, as an example I'm giving you, let us try to take one of the example, which is this. Let us try to take one of the example, which is this. Let us try to take this as an example to understand. Okay, so the example is, let's say I'm writing a matrix which is like minus 1 1 1 1 minus 1 and 1, and then 2 1 and 2. Okay, let us say this is 1. So what would be the characteristic polynomial? So characteristic polynomial, we did it yesterday. This particular matrix we did yesterday, and the characteristic polynomial came out to be lambda cube minus 7 lambda and minus 6. If you remember, I did this particular question yesterday only. So that I'm taking the same example. If I take the same example, I know that I will not have to bother about finding the eigenvalues. This is an example that I took yesterday. So even if you're not getting it, please, I hope you can do it on your own. Now, in order to find A inverse, first let us verify the first let us replace instead of lambda A, because by Kelly-Hamilton theorem we know that every matrix satisfies its characteristic equation. So you will get a cube minus 7a minus 6 identity is equal to 0. And if I want to find A inverse, the A inverse would be what? If I want to find A inverse would be what? So your A inverse would be simply, I think it will be equals to 1 upon 6. I think this will be, if I take this on this side, it will be simply A square minus 7 times identity. So this will be your A inverse. This will be your A inverse. So you can readily find A square from here. You can place identity, and then you can find an answer. I'm leaving the answer for you. I hope you will be able to do it. So answer would be, I think, 1 over 6. It's a long question. I don't want you to write it. I think this is something that you can do on your own also. Okay, so this is your A inverse. I hope it is clear. Okay, now what happens is, this is your characteristic equation. Now, a definition that I'm right now giving to you, I'm not elaborating much on that, but just actually it will be very helpful when you will be doing diagonalization. Okay, I'll speak a little bit about this particular polynomial in linear algebra also, but right now just giving you a slight motivation. Okay, slight motivation. Now just think about it. That it may so happen that A has repeated eigenvalues. It may so happen that A has repeated, and it not only satisfies your KellyHamilton theorem. It not only satisfies the KellyHamilton theorem, or you can say it not only satisfies the characteristic equation, rather it also satisfy a polynomial of a lower degree. And this particular polynomial is called as a minimal polynomial. Just remember, this polynomial is called as the minimal polynomial, and we'll speak about this in quite detail when we'll be doing diagonalization and stuff like that. So this is called as a minimal polynomial. Okay. So basically, what does it imply? It implies that, let's say your matrix is of n cross n. Your matrix is of n cross n. Then you can expect its characteristic equation to be of. Order n or degree n. Okay, so this is your characteristic equation of degree n. Now what happens is, as I told you, when there are repeated values, it may so happen. It's not always necessary, but it may so always happen. So it is not always. I'm not writing that it will always happen. It may so happen. That is, you can say that quite often it may happen that A has repeated eigenvalues. Then it not only satisfies the characteristic equation, rather it also satisfies the minimal polynomial. What is a minimal polynomial? Minimal polynomial is a polynomial which is of the lesser degree than the characteristic equation. So for a n cross n matrix, the characteristic equation will be of n degree. However, whenever you have it may so happen that when the eigenvalues are repeated, let's say eigenvalues are repeated, then A also satisfy another polynomial which is called as the minimal polynomial. It also satisfies a minimal polynomial. I'll show you all these things with an example. Don't worry. And here the degree of m will be less than degree of n. So degree of m will be less than degree of n. I hope it is clear. However, note that from mathematics point of view, the converse is not true. That is, I have written that it may so happen that if eigenvalues have eigenvalues have repeated, eigenvalues are repeated, then there is a possibility of a minimal polynomial. But existence of repeated eigenvalue does not necessarily imply. So I'll write it. Note. I'll write it basically, because otherwise you'll get confused. I will write it. So as a note, I'm writing that the possibility of a minimal polynomial of degree n, possibility of a minimal polynomial of degree n, degree m, sorry, no, degree n, degree m, that is m less than n, arises, and this is what I'm writing, possibility. Okay, it may so happen, arises only if A has at least one repeated eigenvalue. Okay, however the converse part is not true. By which I mean that I'll write it in different pen. By which I mean that the existence of repeated eigenvalue does not imply the existence of minimal polynomial or m less than n. It may so happen that your minimal polynomial can also be the characteristic equation. It may so happen that minimal polynomial is equal to the characteristic equation for the case of repeated eigenvalue. It may so happen. So please remember, the converse part is not true. I know this is slightly confusing for you, so I'll help you this using one of the examples. So if I'll give you an example, you'll be able to understand. Don't worry. Let us, and I'm not right now. I'm not telling how to find minimal polynomial. Right now, I'll be giving you an example, and I'll be supplying you with the minimal polynomial so that you can verify. So let us say I'm taking one of the example. Can I ask that everybody is getting till now? Can I ask that everybody is getting the concept till now? So are you all getting the concept till now? So as I told, what I'll be doing, I'll be actually explaining you this using an example. Okay, good. So just don't worry. I wanted to explain that existence of repeated eigenvalue does not imply that m is supposedly less than n only. It may so happen that your minimal polynomial can even be equal to the characteristic polynomial. Even when you have repeated eigenvalues. Let's say I will give you one of the example. So let's say this is your example 2 0 0. You have 0 2 0 0 0 2. Okay, so this is a diagonal matrix. What do you expect your characteristic equation to be? So your characteristic equation I'm writing here. So your characteristic equation would be Your characteristic equation would be lambda minus 2 whole cube. This is quite easy to see that. I think you will be able to find this. This is very easy. I told you if the diagonal, if it is a diagonal matrix, then the corresponding eigenvalues lie on the diagonal side, and all of these are 2, 2, 2. So I can write the characteristic equation would be lambda minus 2 का whole cube. But just think about this. But think about this. Think about this. What would be the can I not write a minus 2i is equal to 0? Can I not write a minus 2i equal to 0? Just think about it. Yes or no? If a minus 2i is equal to 0, clearly you can see a minus 2i is equal to 0. A is this. Let's say this is your a. And if I subtract my a with subtract my a from, so if I subtract 2i from my a, what I'll get? I'll simply get 0. What does it imply? It implies that this also satisfies, this particular A matrix also satisfy this equation. Right? So this particular you can say matrix A also satisfies this. Clearly the degree is lesser than this. So what is this? This is the minimal polynomial. This is what is referred to as minimal polynomial. This is what is referred to as minimal polynomial. Are you getting my point? Again, let us take another example. This is one of the example. Let's say 1. Let us take another example. I'm right now supplying you minimal polynomial because then you'll not be able to. I just don't want to make it more rigorous. I just want to explain you a definition right now. We'll discuss all these things when we'll come to diagonalization. Okay. Now let us take another example. Let us take another example. Let's say b. And let's say b is equal to what? Let us say b is equal to this is, let's say 2, 1, 0, and you have 0, 2, 0, and then you have, let's say 0, 0, 2. Let us say this is your b. Okay, and I want to say that what would be characteristic equation for this? I want you to take your time little bit and try to find the characteristic equation. Try to find the characteristic equation. I know characteristic equation can be found as 2, 2, 2. You can just think if I replace b minus lambda I modulus, and clearly you can see that if I expand my determinant through here, so it will come as 0. If I expand my determinant through here, it will come out as 0. Only my determinant would be expanded from here. So characteristic equation would come out as lambda minus 2 whole cube only. I think it is quite easy to see, because see, if I write minus lambda, minus lambda, minus lambda here, if I take a determinant, you can see that if I expand through a, so this would be 0. If I expand through 0, obviously this is 0. Then obviously I can expand my determinant only through 2. So it will be 2 minus lambda into 2 minus lambda whole square. So it will be lambda minus 2 whole cube equal to 0. Or I mean 2 minus lambda whole cube also you can write, but I'm taking a negative common out. Is that clear? Please tell me whether you are confirmed, whether you can say that this is right or wrong. I mean, are you confirming this, that the characteristic equation is lambda minus 2 whole cube for matrix B? Can you confirm me that the characteristic equation will be lambda minus 2 whole cube? I think this is quite clear. Okay. Now you see, I'm doing just one thing. Let's say I want to find b minus lambda I whole square. What it will give me? So what it will give me? So b minus 2i whole square. B minus 2i whole square would be equivalent to writing 0, 1, 0, 0, 0, 0, and you'll get 0, 0, 0. Okay, isn't it? So b minus 2i would be what? It would be simply 0, 1, 0, 0, 0, 0, 0, 0, 0. And again I can write 0, 1, 0, 0, 0, 0, 0, 0, 0. This is equivalent to writing square. Okay, now what will happen from this? If you just try to find this you'll get a null matrix from here. You'll get a null matrix. Null matrix. So what do I say? I can say that my b not only satisfies this equation, my b also satisfies this equation, that is lambda minus 2 whole square. So my b not only satisfies, my b will not only satisfy lambda minus 2 whole cube, rather it also satisfies lambda minus 2 whole square. So this is your minimal polynomial. This is your minimal polynomial here. And for another matrix C, I will write here another matrix C, let's say. And if I write matrix C here, so matrix C would be what? Matrix C would be, let us say, it is equals to 2, 1, 0, 0, 2, 1, and you have 0, 0, 2. Here you can have no other choice, but here your characteristic equation will also be lambda minus 2 whole cube, and your minimal polynomial is also lambda minus 2 whole cube. Here you have no other options. Okay, I have not taught you how to find minimal polynomial, but I am just stating you the minimal polynomial. So for B, the minimal polynomial would be lambda minus 2 whole square. For the matrix A, the minimal polynomial would be lambda minus 2i, which is quite evident itself. Lambda minus 2. For C, the minimal polynomial is equal to the characteristic polynomial here. So here you can clearly see that the eigenvalues are repeated, but still m is not less than n. So here your m is in fact equal to n. So here m is equal to n. So here minimal polynomial is equal to the characteristic polynomial. That is, the degree of the minimal polynomial is not less than n. Although the possibility of having a minimal polynomial will occur only if your eigenvalues are repeated, but it is not always necessary that the existence of repeated eigenvalue imply m less than n. That is, existence of repeated eigenvalue not necessarily imply that there exists a different polynomial other than characteristic equation of a degree lower than the characteristic equation. It may so happen that even if you have repeated eigenvalues, then minimal polynomial may so happen to may be of the same degree as that of the characteristic equation. This is what I want to convey. I hope it is clear. I know I have not taught you right now how to find minimal polynomial, but just for right now, just for the definition's sake, are you getting my point? Okay, so I hope everybody is getting the point. Now let us do some questions. Let us do one more important application. So one of the application that I taught you was this. So one of the application was to find the inverse. So for Kelly-Hamilton theorem, the first application was finding the inverse. Right? Now second application, probably when we'll do diagonalization also, then we can know. But in general, to simplify the function of a matrix. To simplify the functions of a matrix. This is yet another way in which your Kelly-Hamilton theorem is very important, right? So right now I have not taught you the functions of a matrix, but still I'll give you one example, and here you can use that particular Kelly-Hamilton theorem, and then when we'll do the function of matrix, that is a different aspect altogether. So I'll define it for you here. Okay, so let us define a matrix A such that a square is equal to identity. A square is equal to identity. And let us define an exponential of matrix. Exponential of matrix e की power iota alpha a. And this particular matrix, I'll write it here. This particular matrix will occur in quantum mechanics only. So you'll find the application of this matrix in quantum mechanics. And in quantum mechanics, specifically in the effect of a rotation on the states of a particle with spin half. Okay, so basically in quantum mechanics, a structure like this you'll happen to see. There you will have a rotation matrix given by A, which is equals to exponential 1/2 iota theta sigma, where sigma is the Pauli matrices dot n cap. So you will have a exponential of a matrix. So you'll have an exponential of matrix whenever it will be required. So I'll teach you all these things when I'll be doing quantum mechanics, but just for the sake of resemblance I have written. So now let us come back to the topic. Let us define exponential of a matrix e की power iota alpha a by what? By a series. That is 1 plus iota alpha a plus 1/2 factorial iota alpha a whole square plus 1/3 factorial iota alpha a whole cube, so on and so forth. Okay, now you see, if I had defined this exponential iota alpha as sum of all these things, what can happen? Since I know that my a square is equal to I, let's say this is my you can say this is my minimal polynomial. Let's say this is my minimal polynomial here. Let us say this is my, I'm writing minimal polynomial. I'm not writing that this is my characteristic equation. Right now I'm writing, let us say that this is my minimal polynomial. Now by actually this minimal polynomial also we can do simplification of this matrix. Let us see how. If the minimal polynomial is given to be equal to a square equal to I, what I can do, I can multiply both sides with a. So if I multiply both sides with a, what I'll get? I'll get a cube is equal to a, right? Again, if I multiply, then I'll get a raised to power 4 is equal to a square. What I will get? I will get a raised to power 4 is equal to a square. And what is a square? A square is again I. So what will happen? In the expansion of this exponential matrix, what will happen? The even power of a, which I can write a raised to power 2m, will become identity, and odd power will become simply a. The odd powers will simply become a. The odd powers would simply become what? A. So what I can do, I can simplify this matrix. So by help of the my mistake, I told characteristic equation, by help of the minimal polynomial, I can simplify the matrices also. So for example, here if I use a square equal to identity as my minimal polynomial, if this is the minimal polynomial given to us, let's say if a matrix A is such that it satisfies the minimal polynomial a square equal to I, then this can be used to simplify the exponential of a matrix. Let us see how. So I know that if I write exponential iota alpha in terms of series, then what it will be equal to? It will be equals to, instead of 1, I will write identity here in order to preserve the order, and then here I will write plus iota alpha a. What will be a square? I told you a square will be again identity. Okay, so it will be minus of alpha square upon 2 factorial identity, minus of alpha square upon 2 minus of alpha square upon 2 factorial times identity. Then what would be this? This will be plus 1/3 factorial. You will have I think there would be a negative outside, there would be alpha whole cube, and then there will be a cube, and a cube can be written again equivalent to a. What would be the fourth term? The fourth term will be 1 upon 4 factorial. Iota raised to power 4 is 1. What is alpha raised to power 4? It will be alpha raised to power 4, and then a raised to power 4 will be again identity, so on and so forth. So if I collect these two terms, what will I get? I will simply get that e raised to power of iota alpha a is equals to what? If I take identity common out, then this will be 1 minus of alpha square upon 2 factorial plus alpha cube upon 3 factorial, and then there would be infinite series all along. Then if I take a common, then what I'll get? I will simply get iota alpha, and I take alpha also common out, then iota also common out, then I'll get alpha minus alpha cube upon 3 factorial, then I'll get plus alpha raised to power 5 upon 5 factorial, and then there would be continuing series throughout till infinity. What is this, by the way? This is sine alpha, and what is this, by the way? This is cos alpha. So what I can say that my exponential iota alpha a can be written in terms of cos alpha and sine alpha for the matrix A whose minimal polynomial is a square equal to identity. So I can write exponential iota alpha a in terms of cos alpha and sine alpha. I hope it is clear. Please let me know if it is clear. Okay, and this particular matrix we'll use it quite often in at least spin related you can say theories. When we'll do spin in quantum mechanics, there you will find this application there. I hope it is clear. Please let me know. Okay, now let us do a few questions so that at least the I think there was some boredom creeping in. So if you're getting bored, then let us do a few questions, and then you'll be able to understand things. Okay, sorry, this is not power 3, this is power 4 upon 4 factorial. Sorry, see, this is power 4 upon 4 factorial. Sorry. So x alpha ki power 4 upon 4 factorial. Okay, so alpha ki power 4 upon 4 factorial. Okay, I hope it is clear now. See, identity now. So identity we have to take common out. This would be identity. This would be identity. Okay, I think it is clear. Is that clear, guys? Please, tell me quickly. Okay, so people have got the question. Now let us do a question, and then we'll go a little bit more ahead. Okay, now try to do this question for me. Okay, just try to do this question for me. I hope everybody is getting. Okay, so let us do this question. So let A be a 4 cross 4 matrix. Let A be a 4 cross 4 matrix with real entries, with real entries, with real entries such that -1, 1, 2, -2 are its eigenvalues. Are its eigenvalues. Are its eigenvalues. If b is equals to a raised to power 4 minus of 5 a square plus 5 I, then which of the following statement is an R correct? Which of the following statement is an R correct? Which of the following statement is an R correct? Okay, now think about this. Let A be a 4 cross 4 matrix with real entries -1, 1, 2 and -2 being its eigenvalues. So A's eigenvalue are given to us. B is related to A as A raised to power 4 minus 5A square plus 5 identity. Then which of the following statement is an R correct? Option number 1, determinant of A plus B equal to 0. Option number 2, is simply determinant of B is equals to 1. Option number C is trace A minus B is equals to 0. And option number D is trace A plus B is equal to 4. Okay, just try to do this question. Try to do this question. Just think about it. Just think about it. I'm giving you 2 minutes or 3 minutes just to think about it. Okay, so I hope have you got an answer to this? Can you mark options in the comment section? Just mark the options in the comment section. Option C, yes, indeed. I think. Just let me. Okay, more than one option correct is here in this question. More than one option is correct, so you can have more than one option. So think about that. There can be a possibility that more than one options are correct. Okay, so option. So there can be more than one option correct. Okay, so let me do it for you. A few of the things probably you may not be knowing. That's why you're not getting an answer to this. Let me do it for you. Okay, so see, always remember, I have told you simply that here I've simply told you. Just remember one thing. So if the eigenvalues of A are what? Eigenvalues of A are given to be -1, 1, 2, and -2, right? This is what is your eigenvalues of A, and we know that B is satisfying a equation. So I can say that sorry, B, the eigenvalue of B uh, will be can be written as lambda ki power 4 minus 5 lambda square plus 5, right? Minus 5 lambda plus 5, isn't it? Yes or no? Is that clear or not clear? I hope it is clear, not clear. Okay. Okay, if that's not clear, let me help you with another question. So I'll help you with another question at first, and then we'll move to this question. So I think most of the people are not getting this question. Okay, so I'm dropping the discussion for now, because otherwise you'll not be able to get what I'm saying. Okay, so I'm dropping the discussion right now. So first let us do easy problems first. Okay, I think it would be easy for us to do. So right now I'm dropping this problem because I hope that people are not getting difficult stuff. Let us do some easy stuff first. Let us do some easy stuff, because I don't want to raise the level so that then things you're not getting, then things you'll not be getting. Okay, so let me do it tomorrow, but let us do a few more questions for your exercise at first. So let us do a few more questions for your exercise. Otherwise, you'll not be able to get these difficult questions. So let us do some easy questions first. Okay, chalo. So let us do some easy questions first. Okay, because probably it will involve some difficult concepts, and that I think I need some little bit of background for that. Now let us do a few questions and then we'll go ahead. Okay, let us do a few questions and then we'll go ahead. Okay, just try to find this simple question. Just I'm giving you a simple question now. Okay, little bit simple question first and then we'll go to this. I think time is up, so I'll do this question tomorrow. I think there are a few concepts that you may not be knowing, so I'll let you know those concepts, and then probably that will become very easy for you. Okay, so now for now just do one questions, do some questions. So for example, if the matrix A is given to you equivalent to 1 upon root over 2 iota 1 1 and iota. Okay, if the matrix A is given to you as iota 1 1 and iota and root 1 upon root 2 in front. What is happening? Just give me a minute. Okay, just okay, so let us say that this is your matrix iota 1 1 and iota, and here it is written 1 upon root. Okay, here it is written 1 upon root 2. Then the eigenvalues of m, eigenvalues of A, sorry, then the eigenvalues of A, option number 1, real and positive. I think first let us do easy question. Real and positive. Option number B, purely imaginary with modulus 1. Purely imaginary with modulus 1. Option number C, complex with modulus 1. And option number D, real and negative. Just think about it. Let us do some easy question first and then we'll move to this. So this is slightly difficult. And probably I will have to develop concept of diagonalization also. So till now I have not introduced the concept of diagonalization. Actually I thought that problem is easy, but then I thought how to relate my eigenvalues. So I will have to use the concept of diagonalization here, or probably similarity. So probably I have not taught you similarity. That is why I think it will not be very fruitful right now to do this question. But remember, in physics, many times you will find the questions are being asked from the similarity concept or concept of diagonalization, because this is very important for us. So please do remember this question. I'll do it for you tomorrow, but right now we'll do some easier questions. Okay, so this question was asked in your JAM exam. Try to do this. So if you try to find the eigenvalues, the question is about what will be the nature of the eigenvalue, whether the eigenvalue will be real and positive, whether the eigenvalue would be purely imaginary with modulus 1, whether it will be complex with modulus 1, or whether it will be real and negative. So if I try to find the eigenvalue equation, let us always remember, what students make a mistake, they actually don't take this 1 upon iota inside. Please take 1 upon iota inside, otherwise you'll get a wrong answer then. So 1 upon iota minus lambda whole square, iota upon root 2 minus lambda whole square minus 1 upon 2 is equal to 0. Okay, so think about this. I think this is very. Okay, so let us solve this. So I'll get what? I will simply get from here lambda square. So otherwise I can do here plus minus 1 upon root over iota, and not even lambda square I will do. I know this is so iota upon root 2 minus lambda. Iota upon root 2 minus lambda is equal to plus minus 1 upon root 2, and so lambda would be simply equals to 1 upon iota 1 minus plus I think there is a problem with something. Okay, just give me a minute. I think there is a problem with something. Okay. Actually, there is something that is eating my space right now. Okay, that is why this has become very slow. Okay, so this would be I don't know what is happening. So this will be lambda is equal to 1 upon root 2 1 minus plus iota. So it can, so this is 1, and we know that what is modulus of complex number is 1 square plus again 1 square. Just think about it. So the what is, so if I'm giving you a complex number which is x plus minus iota y, the modulus of it will be root over x square plus y square. So clearly the modulus here would be equals to what? Root over 1 square plus 1 square, which is root over 2, and 1 over root 2 is here. So I can say that the modulus of my eigenvalues would be 1. So my eigenvalues would be complex. My eigenvalues would be complex with modulus equals to 1. With modulus equal to 1. With modulus equal to 1. I hope it is clear. So option would be complex with modulus 1. Now let us do another problem. The problem says find the inverse of the matrix M. Find the inverse of the matrix M. So matrix M is given by 0 1 1 0 0 1 and 1 0 0. So this is your matrix. We are told to find the inverse of M. So what would be inverse of M? Let us first apply the KellyHamilton theorem. So what does our KellyHamilton theorem says? KellyHamilton theorem suggests us to solve this m minus lambda I equal to 0. And if I find m minus lambda I to be equal to 0, then I will get a characteristic equation, and I know that every matrix satisfies its characteristic equation. So I'll get minus lambda 1 1 0 minus lambda 1 1 0 and minus lambda, and this is the determinant. And now I want to find the the characteristic polynomial from here. So what would be my characteristic polynomial? This would be minus lambda, and then you will have lambda square. So minus lambda square, then you will get 0, and this would be simply so let us find this. Okay, so the characteristic polynomial would be minus of lambda cube plus of lambda plus of 1 equal to 0. Now I know that my characteristic polynomial I can replace instead of lambda m, because my Kelly-Hamilton theorem says that what? My Kelly-Hamilton theorem says that matrix satisfies the characteristic polynomial. So if I use this, I'll get minus of m cube plus m plus identity is equal to 0. Or I can say that my m cube minus of m minus of identity would be equal to 0. Now pre-multiplying it with m inverse, I will get m square minus of identity minus of m inverse. And this will give me what? It will give me m inverse. So inverse of m would simply be equals to m square minus of identity. I hope it is clear. This is something that I think everybody can do at this level. Is that clear? Another question that was asked. Try to find this. Try to find the eigenvalues of the matrix given by. Try to find the eigenvalues matrix cos theta minus sin theta and cos theta. Let us try to find the eigenvalues for this matrix. Okay, and options now I'm giving it to you. Option number 1, 1 upon 2 root 3 plus minus iota when theta is equal to 45 degrees. Option number B, 1 upon 2 root over 3 plus minus iota when theta is equals to 30 degrees. Option number C, plus minus 1 since the matrix is unitary. Then option number D, 1 upon root 2 1 plus minus iota when theta is equals to 30 degrees. Okay, so let us do this particular problem. So I taught you this particular problem. See why? I told you that whenever you are going to have this particular matrix is nothing but what it is. This is your rotation matrix. If you remember, we did today rotation matrix in particular. So this is your rotation. This is your rotation matrix. And always remember, then whenever I'm going to talk about rotation matrix, let's say if it is a 2 cross 2 matrix, I told you in the morning, that is in the initial session, that the rotation matrix eigenvalues are nothing but it is equals to e raised to power plus minus iota theta. So the eigenvalues for the rotation matrix are e raised to power plus minus iota theta. Now there are different options given to you. This is something that I will recommend you to remember, because this will be used quite often. So please remember this particular matrix. So the eigenvalues for the rotation matrix is e raised to power plus minus iota theta. Okay, so it will be equals to plus minus 1, no. Okay, so now this is clear. Now what you have to do, just place theta value. So let's place theta is equals to 30 degrees. So the eigenvalues for theta equals to 30 degrees will be what? So it will be equals to cos of 30 degrees plus minus iota sine of 30 degrees. What is cos 30? Cos 30 is simply 1 upon 2. Cos 30 is simply root 3 upon 2. And then plus minus iota. What is sine 30? It is 1 upon 2. So answer would be take 1 upon 2 common out and you will get root 3 plus minus iota. So I think option number B is the correct answer. Okay. Okay. Now let us do another question. And this question is again based on eigenvalues only. So the eigenvalues of the matrix eigenvalues of the matrix A given by 0, iota, and 0. Eigenvalues of the matrix given by 0, iota, 0 are 1. Option number A given to you is real and distinct. Option number B given to you is complex and distinct. Option number C is complex and coinciding. Complex and coinciding. Option number D is real and coinciding. Real and coinciding. So let us do this problem. Okay, so in this particular problem, again, try to find the characteristic equation at first. So characteristic equation would yield you eigenvalues. So this will be minus lambda whole square minus of iota whole square. So minus lambda whole square minus of iota whole square equals to 0. So you'll get lambda square is equals to, this would be iota square is minus 1, this would be simply minus 1 there. So you'll get lambda is equals to plus minus iota. If lambda is equal to plus minus iota, it implies what? It implies that the eigenvalues are complex, but they are distinct. Eigenvalues are complex, but they are distinct. Option number B is the correct answer. Okay, now let us do one more interesting question. That is again, I think these all questions are usually asked in GATE, so it's not that difficult. Also, that you may be able to do it. Don't worry. Okay, so this particular question was asked in GATE. It is written that an 3 cross 3 matrix has elements such that its trace is 11, and its determinant is 36, and its determinant is 36. The eigenvalues are all known to be positive integers. It is known that all the integers are positive. All the eigenvalues are positive integers. The largest eigenvalue of the matrix, of the matrix. So largest eigenvalue of the matrix is option number A 18, option number B is 12, option number C is 9, and option number D is 6. Okay, so how to go about it? So see, it is given that the 3 cross 3 has elements such that its trace is 11 and the determinant is 36. So I can write that my sum of eigenvalues is, so I can write that my sum of eigenvalues, which is equals to trace, I can write lambda 1 plus lambda 2 plus lambda 3 is equals to what? It is equals to 11, and my determinant is 36. My determinant is 36. That implies my lambda 1 into lambda 2 into lambda 3 is 36. Okay, and now it is given to us that all of them are known to be positive integers. So what I can do, I can do a certain guesswork with regards to this 36. So 36 can be generated by 1, 4, 9. Okay, it can be generated by 1, 4, 9. If you write now, and now you can permute also, so it can be 1, 9, 4, and all those things can be there, but I'm just telling you one combination can be 1, 4, 9. You can commute all these things, so you will have a 3 factorial kind of thing. So I'm just giving you the groupings. So I'm not permuting them, I'm just giving you the groupings. So one of the grouping can be 1, 4, 9. Another grouping can be 2, 2, 9. Just think about it. 2, 2, 9. Okay, another grouping can be let us say it can be 4, 1, 9. It has been done. Another grouping can be 36. So 2, 3, and 6. Another grouping can be 2, 3, 6. Okay, if you use 4, then 4 into 9 will be there. If you use 5, 5 cannot be there. So overall there can be several other groupings, but you have to also think that which of the following conditions satisfies the trace. So if you find the trace from here, 9 plus 4 is 13 plus 1 is 14. No. 9 plus 2 is 11. 11 plus 2 is 13. No, not at all. So 2 plus 3 is 5. 5 plus 6 is 11. So this is the correct answer. So the possibility would be that your one of the eigenvalue is 2. Another eigenvalue is, let's say, 3. And another eigenvalue is 6. So the determinant will come out as 36 and the trace will also come out as 11. So the largest of the eigenvalue would be 6 in this particular case. Since only integers were allowed, if integers were not allowed, then things would have changed. Let's say root 6 ka whole square. Let's say 6 raised to power 1 by 3 ki power 3. Okay, so I hope all these questions you are getting. Now let us do one more question, and that is the final one. Let us do one more question, and that is the final one. Okay. Are there any people present in the class right now? Okay, so question says that a 2 cross 2 matrix A 2 cross 2 matrix A has eigenvalues e raised to power iota pi over 5 and e raised to power iota pi over 6. So these two are your eigenvalues. The smallest value of n, such that a raised to power n is equals to identity. The smallest value of n such that a raised to power n is equals to identity. Option number 1 is 20. Option number 2 is 30. Option number C is 60. Option number D is 120. Now, in order to do such questions, you just need a little bit skill. I mean, you just don't have to complicate things. You just have to use two of the concepts that I have taught you. Just use two of the concepts and then you will be able to understand what I want to say. So see, if I have to do this question, again I told you, see, what does it imply? So I'm just doing it for you. The question is, a raised to power n is identity. I told you that if the, I'm writing it here, if the eigenvalues for a are lambda, eigenvalues for a are lambda, then for a raised to power n, the eigenvalues would be lambda raised to power n, right? And now you have this and this. There are two eigenvalues. Let us denote them by lambda 1 and lambda 2. Okay, and here you have this identity. So identity is 1 1 0 0 is equals to, okay, this. Okay, now trace of this matrix A raised to power n would be what? The trace of A raised to power n would be lambda 1 raised to power n plus lambda 2 raised to power n. And it will be equals to what? Trace of identity also. It should be equals to trace of identity. Trace of this matrix is equals to trace of identity, which is equals to what? 2. So what does it give me? It yields me that e raised to power iota n pi upon 5 plus e raised to power iota n pi upon 6 should be equals to what? It should be equal to 2. It should be equal to 2. This is one thing. Second thing that you are getting is that if I do a determinant on both of the sides, if I take a determinant here and determinant here, so what it will give me? It will give me that determinant of a raised to power n should be equals to 1. Okay, this is what it means. And I already know that determinant of a matrix is equals to the product of eigenvalues. So it equals to lambda 1 raised to power n and lambda 2 raised to power n, and this should be equals to 1. And what is lambda 1? I know lambda 1 is e, so it will give me e raised to power iota 11 pi, not 11 pi, I think 11 pi upon 30, right? It will give me 11 pi upon 30 times n is equals to 1, right? And now I have to find the least value of n. I have to find the least value of n such that it will give me this. So what should be the least value of n? You should remember that e raised to power of iota 2n pi is equals to 1. You should remember this. So basically, if whatever is accompanying iota, if it is even, then things would work. So what all values can give you an even multiple here? So 120 can give you, even 60 can give you, 30 cannot give you, forget about this, 20 cannot give you, forget about this. So among both 60 and 120, what is smallest? 60 is smallest. So you can clearly see that 60 would be answer, I think. See, if you write 60 here, you will get 30, cut 30 will cancel this 62 times, so that is 22 pi. So e ki power iota 22 pi. E ki power iota 22 pi would be what? So if you write e ki power iota 20, if you use n equals to 60, you will get e ki power iota 22 pi. And what is e ki power iota 22 pi? It is 1 only. And if you replace this here also, you will get the same thing. So if you replace it here, so if you replace 60 here, so e ki power iota 12 pi is 1. And if you replace 60 here, you will get e ki power iota 10 pi. It is 1. 1 plus 1 is 2. So both of them are conforming to the same thing. So the least value of n should be equals to what? It should be equals to 60. Okay. So I think it's enough for today. I hope to meet you tomorrow. Till then, kindly revise all these concepts. One of the problems I have dropped Why did I drop it? Because I thought initially that that can be done by the basic knowledge of eigenvalues, but later on I understood by after giving the problem that probably a concept like diagonalization is also required there. So we'll do diagonalization and then we'll come back to the same problem. So don't worry. And two of the problems are I have also skipped from the lectures of your I think rank, and rank also we need to see in perspective with in perspective of your consistency of equations also. So a few topics are left, and from tomorrow we'll start with eigenvalues of some special matrices. So please come in the class. Please remain responsive in the class, and once you remain responsive, once you give me answers to, like, even if you're not getting, write not getting, so that uh, I'll be interacting more. Okay, so I hope to see you tomorrow. Till then, take care. Bye.